Bumpy Labs, and this is your front door to innovation. So, what Bumpy Labs does is it helps you build, run, and analyze complex simulations without the need for a code. Now, this is your entry to the simulation hub. What we mean by the hub is that this is a digital scientific workbench. It's designed to be familiar and efficient, and it is a storehouse of all the simulations you will build over time. Right? So let's see how this looks like. But before we enter the door, let's have a quick overview of what this can do. It can You can upload research papers, which will be able to extract your simulation parameters, equations, and generate data using uh, advanced LLM models. Once the PDF is well analyzed, it will be able to extract all the parameters from um, your paper or any document you upload, and it will be able to do this through a agentic workflow, which means the AI agents will plan the entire analysis strategy for you, do the analysis, extract the parameters, then it will be able to look at some similar other literature, and that way it will become more and more robust in its simulation capabilities. All this is happening real time, and it's built on popular scientific computing libraries. And the best thing is you'll be able to do some very interactive visualizations. So let's launch the platform. Okay. So let's try to upload a PDF. We'll upload a Elasto Inertial paper. So just to show you how that paper looks like. So this is a paper on Elasto Inertial microfluidics that we'll be analyzing right now. And this is based on bloodstream infections. But the simulation part of this paper is focused on first normal stress differences that you see here. And this was based on a COMSOL simulation where we are showing some first normal stress differences of non-Newtonian fluid in flow. It took the researchers probably days or weeks or months to kind of come up with this kind of a simulation, right? Now we'll try to do that much faster. And the idea is we'll follow the physics that is kind of part of this paper. We'll expect the LLMs to extract the physics out of it, construct the prompt recipes that power this platform is actually extracting the physics recipes, it extracts parameters, and it will be able to construct the simulation for you. So this will go through the loop. It has uploaded the paper. Now it will extract the parameters. You can see the upload is successful. And this paper I had uploaded earlier also, but now we again do the run. It's the same paper that I showed you right now. So let's try to make this run, right? So these are the parameters that has been extracted, and then the previous run that we had kind of customized a different set of parameters. So that is advantage, and that's also to show you that in the library you can basically configure multiple simulations in different ways, right? So this is where we are defining the height, then the length of the microchannel, then the particle size, we'll keep it as 5 micrometers. And we have some flow rate. Let's give it some good flow rates, right? Around 800 microliter per hour. The Reynolds number is typically low for this kind of study, so let's keep it around 9. And the Wiesenberg's number is high, so let's keep it around 3. And the ppf concentration, so this was based on non-Newtonian fluid, which was PEO, and that was the binding force for the particle focusing, right? So we'll configure our analysis based on that. And once we configure, we have multiple possibilities. We can do a time series analysis, a parametric study, sensitivity analysis, where we're kind of quantifying the impact of each parameters, some spatial distributions, where we have contour plots, heat maps, etc. Optimization of parameters. So there are multiple things you can do. For now, we'll just stick to a custom analysis. And the custom analysis goes something like this. So this is the analysis we'll do. We have given some theoretical background of elastoinertial microfluidics. which means that the elastic forces on suspended particles direct them towards the center and four corners of the microchannel. And the migration of the particles is the result of this non-uniform normal stress differences, right? Then we have given how the first and stress and second normal stress differences look like, and all the notations that are describing that. Then the elastic force is given by the cube of the particle size. And then we have also mentioned what is the relaxation time in non-Newtonian fluid. And then the kind of forces that are in play here, right? These are all the specifics of this particular simulations, and we don't need to go too deep into it. But let's say now what we're telling the tool BumpyLabs to do is if it can analyze the trajectory of a particle that is introduced at 0.5 times the radius of a pipe based on the info in the paper with similar conditions as in the square channel. So the paper was based on a square channel geometry. Now we have moved to a circular channel, right? So this is the agentic runner mode, the agentic thinking process in action. It starts with some planning. The planner agent is analyzing our request first. So once it's analyzing your request, it's also kind of doing multiple web searches, looking at the user instructions, the PDF content. It has extracted multiple similar papers right now, right? It again looks at your instructions, does some additional searches for context. It again finds some new papers, and this kind of look continues in a loop. It extracts multiple papers. It kind of keeps looking through it. And now after that, the analysis has been configured, right? So now we are in a takeoff stage. We can run our simulation. Okay, so this is how the analysis looks like. And it can be made more advanced, but as of now, it tells you that, okay, the Reynolds number and sort of increases with flow rate, which is kind of understood well. Then the Wissenberg's number is increasing with PEO concentration. And it also tells you something very interesting here. So the particle count seems to be focusing on the center, which is what we would expect when we have like an increase in Reynolds number and a high Wissenberg's number. So that is also kind of shown here, right? And we can kind of keep configuring this to kind of extract our required simulation, but this is like a good start.